the hydrodynamics models, or hydrodynamics, I should say, for floating offshore wind, or relevant topic. And we'll have short presentations this afternoon. So the first one is from Federica Perassi, who works at TUDelft, and she will talk about fluid structure interaction between vertical axis tidal turbine and floating structure. Federica, I think you should.
Yes, here, can you hear me?
Yes, we can hear you.
Okay, wait, I will share the screen. Can you see my screen?
Yes, we can see your PowerPoint.
Okay, perfect. Wait. So hello everybody, I'm a master student of Sustainable Energy Technology at TUDelft, and I will talk about my master graduation project, which is fluid structure interaction between vertical axis tidal turbine and floating structure. So this is the outline of the presentation. First, I will talk about tidal energy and the floating vertical axis turbine concept. Then I will introduce the problem statement and the methodology that I'm using to tackle it. And finally, the case study and conclusions. About tidal energy. Well, tidal energy is a type of ocean energy, and ocean energy is recently being exploited more and more, and European Union objectives are to reach 1 gigawatt by 2030. And in particular, tidal energy is very promising since it is very unpredictable and dependable source, so it can support grid stability, it has large energy density, and it has the potential of decarbonizing coastal nations. And there are several concepts for tidal turbines. The most common one is the horizontal axis turbines on the picture on the right, but also now there is a recent interest in vertical axis concept because of the omnidirectionality, the reduced installation and operation and maintenance cost, but also because it's advantageous for less energetic sites. And also in the meantime, the offshore energy sector is going towards floating structures. From fixed structure, because compared to the fixed structures, you can reduce the cost in installation and operation and maintenance, and you can also exploit the resources in deeper water and minimize the visual impact. So our research is about a floating vertical axis tidal turbine, and the main challenge in studying the hydrodynamic of these turbines is that the floater moves under wave-induced motions in 6 degrees of freedoms, and this induces a change in the forces of the vertical axis tidal turbine because of the change in relative current speed. But in the same time, these forces exerted on the VAT, on the vertical axis tidal turbine, go back to the floating platform, inducing a different response motion. So there is this coupling between the forces on the rotor and the motion of the platform, which is a very challenging topic, and it is relevant for understanding the performance variation in time and the hydrodynamic loads that go from the rotor to the floating platform and vice versa. However, the scientific literature about this topic is very limited. Mostly CFD simulations have been conducted about the hydrodynamic of floating and vertical axis tidal turbines, especially in 2D, so about yaw, surge, and sway. Compared instead to floating vertical axis wind turbines, which has been dealt with more extensively in the research. And in fact, you can see there are for example, momentum models and vortex methods have been used in the literature in order to allow the coupling of the whole system. And instead, for vertical axis tidal turbines, the majority of papers deal with the uncoupled system, either from the perspective of the floater or from the perspective of the rotor. So finally, my approach in my graduation project is first defining and validating a tool different from CFD simulations, in order to reduce the computational time, which is in this case the Fnv vortex panel method, and finally using this method in order to study the hydrodynamic response of commercial vertical axis tidal turbine under intense surge motion. So about the methodology, I've been using this 2D vortex panel code, which was developed by Professor Ferreira from TUDelft. And it is an unsteady method, which allows a simple integration of platforms motion in the code, since it's written in MATLAB. And it was chosen as it is a trade-off between accuracy and computational cost. during a literature review process. And it follows the formulation described by Katz and Plotkin in 2001 in their book of Aerodynamics. And it implements a free wake model, which means the computational time is reduced compared to CFD, but it is still of a few hours because it's still a quite accurate model. And it's been verified in my work with the simulation results from Xu et al. And Wang et al. Who report results about sway, surge, and yaw motion in 2D using, of course, CFD simulations. So the verification allowed me to understand that this 2D vortex panel method is an accurate tool with a reduced computational cost, which can be compared to the result to 2D CFD. However, the 2D panel code assumes implicit flow, which means the loads predicted by this code are slightly larger. And two possible solutions, I can think of two possible solutions, which are or either correcting for viscous effects or considering this panel code a fast and conservative design tool. And finally, it's worth mentioning that the 2D panel code was chosen as it is a method which has a very clear physics and very clear computational steps. So it is easier to use these methods compared to CFDs to understand what's happening to the aerodynamic of the turbine. And finally, I've been working on this case study, which is with this commercial turbine. You can see on the left the geometry and the simulation inputs and setup that I defined through a convergence study and the CP lambda curves computed to find the rotational speed. And we use an intense surge motion simulation to understand properly what was happening at the level of the blades. This is the convention used by the code. So the analysis starts from the force coefficients. Under only rotation motion, you can see that the loads oscillate with a frequency which is, in this case, we have two blades, so it's twice the rotational frequency, because these are the rotor thrust coefficient and lateral force coefficients, and they oscillate between two straight envelopes because of the steady inflow conditions and constant operational parameters. Instead, when you introduce this intense surge motion, what happens is you can see oscillations which are both related in frequency to the surge frequency and the rotational frequency. And you can see the amplitude, of course, is increased, and it increases when the surge velocity is parallel and in the same direction of the current velocity, and it decreases when the surge velocity is opposite to the current velocity, and it leads the coefficients to go around zero. But the origin of this oscillation was also investigated in the velocity triangles, because the 2D panel code works with the logic of velocity triangles used to compute the pressure coefficient, and the pressure coefficient around the blades is used to compute the force coefficients. Therefore, the velocity triangles are studied. And you can see there is an important difference between the only rotation case and surging motion case, because in the only rotation case, you have the flow repeats itself at blade 1 and at blade 2 every half rotation or every full rotation, and instead in the surging motion case you have to wait a longer number of rotations and a longer number of surge cycles in order to repeat the same flow at the blade and at the two blades, making the flow very complex. And a further investigation was conducted on the components of the relative velocity. In particular, you can see in the upper graphs are about the only rotation case, and the lower graphs about the surging motion case. You can see surge affects in amplitude both the induced velocity and the current and displacement velocity, but the displacement and current velocity is mostly affected in amplitude, and instead the induced velocity is mostly affected in spikiness. And it is very interesting to look at the induced velocity, because once you look at, this is, for example, the evolution of the wake, and you can see that the evolution of the wake for the only current case on the left, and instead for the surge case on the right, is very different. And because when you have the displacement of the rotor going downwind, you increase the blade vortex interaction in frequency, which leads to a less smooth graph. When instead you go towards the left, so more upwind, the rotor stops interacting with the wake, so the graph becomes more smooth. And in conclusion, what was found from this research was that the 2D vortex panel method is a conservative and fast tool that can be used to assess the hydrodynamic response of a vertical axis tidal turbine under floating platforms motion, which can be sway, surge, and yaw. And that surge affects the hydrodynamic road response with two contributions mainly, which are the surge velocity affecting the amplitude of loads mainly, and the surge displacement affecting instead the induced velocity and therefore the complexity of the signal and the spikiness of the relative velocity of all the load coefficients. And further analysis is being conducted, so this is a work in progress, and I'm still looking into more details of the flow and also another simulation with a different turbine. So these are my references, and thank you. And if you have any question.
Thanks a lot, Federica, for the very clear presentation.
Stop sharing.
Yeah, I think we will do, if you can stay until the end of the two next talks, what we usually do is that we collect the questions on the Q&A. So I invite everyone to post questions there, and then we will discuss. So we'll split six short presentation into two parts. So yeah, time-wise, maybe around 3 or 2:45, I think we should be able to address them. So please, the audience, do post some questions for Federica. I have a few, but it would be nice to have a nice discussion. So thanks a lot for that. Now I invite Manuel Rentschler from WavEC, and he will talk about CFD code comparison, verification, and validation for a floating wind semi-submersible platform.
All right, hello everyone. Just going to share the screen.
Yeah, we can see it. That's great.
You can see it already. Okay, perfect. Okay, so then hello again, everyone. My name is Manuel Rentschler. I'm research engineer at WavEC Offshore Renewables from Portugal. And I would like to report about our research and the learnings that we have drawn from our CFD work on the hydrodynamics of floating offshore wind turbines. And first of all, this is a collaborative project between WavEC and TUDelft and the University of Tokyo. And that is why I would really like to thank for the support of all the co-authors, especially also to Pranav, who's here in the organization, who has been sharing a lot of CFD work with me on that. So our objective for this work is to verify and validate the CFD codes that we are mostly using at the institutions. And for WavEC, that is the community-based code Refresco, developed by Marin, and our colleagues from Delft were using OpenFOAM. Now comparing CFD codes is not a very trivial work because every code, of course, has its different implementation methods and settings. But for this exercise, we really try to keep the numerical setup as similar as possible to guarantee a good comparison. And in the end, we would like to open the code comparison actually for everyone and for other codes by making available all our input data and the computational meshes that we were using and sharing them on the GitHub link that you will see here below, so that you can actually help us getting better. Now, the test cases that we have selected are decay tests, and first exercise starting with a simple floating cylinder, and in the following then the model scale platform of the Oc4 semi-submersible platform that you can see displayed here at the corner. But before proceeding to the test cases, maybe just in theory, a few words to the terms verification and validation, because it seems that those are words that often get mixed and a bit confused. So what we understand in validation is basically an engineering type task that is targeting to show that the numerical model that we have created is a good representation of the reality. And often we do that by comparing simulation results with experiments. And yeah, as you know, this is widely done in literature. Now, regarding verification, this often seems to be a bit overlooked, and that is why we want to highlight it here. Verification is a purely mathematical task that has the objective to estimate the uncertainty of a numerical result, while we typically don't even know the exact solution, but at least we want to specify an interval in that we say, or in that we are confident that that our results are in there. But how do we get to this numerical error? Well, the numerical error is actually composed of different components, and typically these are the round-off error, the iterative error, and the discretization error. But if we use a double precision calculation, and if we ensure a good iteration of our calculations, then typically we can neglect the first two errors, and the discretization error becomes the dominant one. And this one can be determined, for example, with grid and time step refinement studies, and we were using an approach based on the methods from Likhitha et al., where you will find the paper linked at the end of this presentation. But now to see the test case where we applied this grid refinement study on, this is the simple cylinder test case, and on the bottom of the screen you can see the numerical model of it with the cylinder in this rectangular domain, which is actually mimicking the experimental tests of the in a water tank that we had available, in which actually the heave and pitch decay for this cylinder were exercised. On the domain, you actually see only half of the cylinder, and this is why we applied this symmetrical boundary condition, just to save on computational effort. Now, for the grid and time step refinement study, we created 4 different geometrically similar meshes that were ranging in the number of cells from roughly 60,000 up to 900,000 cells. It's quite a big range, and we also tried with 3 different time steps. Now I will only show you a few results of the heave decay. The pitch decay will be for another time. First of all, a few words to the uncertainty levels that were achieved. So for the natural period, we got the specification of or uncertainty smaller than 2%, which is just very good. For the linear damping coefficient, our uncertainties were getting a little bit larger, ranging for the finer meshes around 10%. And actually, we already saw there some differences coming apparent between Refresco and OpenFOAM, because Refresco seemed to be more sensitive to the grid refinement, while OpenFOAM was more sensitive to the time step refinement. Now, if we were investigating the uncertainties of the oscillation peaks of the heave motion that you see here on the right, those uncertainties were getting even a bit larger, up to 20%, and that is what you can basically see here indicated with the uncertainty bars and in the peaks. Now the result doesn't look so tragic. So often, if you wouldn't see this uncertainty bars, you would hear, this results look quite good. And also, if we look at the values and compare with the experiment, you can actually see that the deviations, they are quite acceptable. But here it is really the verification study and the uncertainties, especially of Refresco, that let us think, can we not improve on this? Should we investigate a little bit further to reduce these uncertainties and improve accuracy? And what was found in further investigation is actually on the left side. You can see a picture of one of the meshes that we initially used. And on the right-hand side, we compare it with the setup that has a lot finer resolution around the edges, around the submerged edges of the cylinder. And you can see only there becomes these vortices apparent around the sharp edges of the cylinder. And that is something that we didn't capture before, and that has actually influence on the results. And we are currently investigating together with the application of viscous layers and turbulence modeling, what exactly those effects are, and if that improves our results. So there is quite some work ongoing in this. But meanwhile, let's jump to the setup for the Oc4 semi-submersible that you can see here displayed in a cylindrical domain at the bottom. Compared to the cylinder, it's quite a more complex structure, but our idea for the meshing was a bit the same as for the cylinder, insofar that for the background resolution, we applied the same refinement that seemed to work fine for the cylinder, only that here, due to the complex structure, we refined a lot around the edges of the platform, and also included a viscous layer for the viscous effects. Now on this model, we were executing the decay tests in 3 directions. I will only talk here about the sway decay, and we will compare that actually with the data from a model scale experiment that was done by our partners in Tokyo. And now showing a little bit the decay motion. If we first have a look at the plot on the right, we can see that Refresco and OpenFOAM were achieving more or less similar results, which is first of all on first sight is a good result. But then if we compare with the natural period and the damping coefficients from the experiment, we can see, yes, the natural period looks good within a deviation of 3%, but the linear damping coefficient is very far off from what we would have expected from the experimental value. And there we needed to investigate a little bit more. What is the reason of this deviation? And one reason is not even numerical, it's just based on how actually do you calculate the damping coefficient. It already makes a big difference. And that is what you here see between θ1 and θ2, if you neglect the first 2 extrema or not. So there we can actually already see a big influence on the damping coefficients that we actually achieve. But it is not only the calculation method of the damping, it is also the amount of freedoms, degrees of freedoms that we allowed. So in the first test, we only allowed 1 degree of freedom because we didn't know the inertial properties of the platform around the other rotary degrees of freedoms, but we estimated them, And if we then apply the 6 degrees of freedom, we can see it actually does make a difference if we apply 1 degree of freedom or 6 degrees of freedom. And actually, we were able to match with OpenFOAM the natural period even better. And depending on which calculation method of the damping coefficient you apply, we are also starting to get to an acceptable level of the damping coefficients. So yeah, as a learning from that, I would definitely say it doesn't make sense to reduce the degrees of freedom allowed in CFD. It's better to use as many degrees of freedoms as possible, because the calculation of a few more equations of motion is really not computationally significant for the million cells for which you solve the Navier-Stokes equations. So more degrees of freedoms always helps. What to remember so far? Code comparison is not a very easy task, and it should be always accompanied with a thorough verification and validation study to reduce the numerical uncertainties. But also it would be, of course, necessary to include the experimental uncertainties, which here were not even known in this exercise. Usually all this have to be assessed and quantified to be able to assess the accuracy and the confidence that you have in your results. Now, the findings from our decay tests, we found that the natural period is something that is rather easy to accomplish, while the damping really seems to be something more challenging, and it's heavily influenced by viscous effects like vortex creation, turbulence modeling. So there is still some work to be done, and actually for the cylinder test case, we will need to revise a little bit the verification study that we have done so far, and hopefully we will be able to reduce our uncertainties. Now, for the Oc4 calculation, we need to complete the 6 degree of freedom simulations for the Refresco. There is currently an issue with the mooring module that cannot handle it, so we will have to implement it and compile it from new. And then we have to compare with the experimental time series, and there we are in contact with Tokyo to get the time series. So then we can apply the same calculation method for the damping coefficients, because if we don't apply the same method, then of course we are introducing uncertainties here that we cannot even estimate. Last of all, this code comparison, it only included 2 codes. So if you have a CFD code that you would like to test, we would be very happy if you help us. And therefore, on this link, I will soon upload the OC6, the OC4 test cases that we were using, the meshes and the setups. And as soon as we have the problem sorted out with the cylinder test case, those will also be available there so that you can do the verification study. So far, I would thank for the computational facilities and the project financing that was only able to support this work. And yeah, thank you all for your interest and looking forward to your feedback. Thank you.
Thanks a lot, Manuel, for the very interesting presentation. So again, please post your questions on the Q&A. I don't see yet any, and I'm sure for both presenters there will be many to come. So please do post them, and we'll treat them in our Q&A session. So now let's move on to the last short presentation of this first part, and this is given by Likhitha Ramesh Reddy from TUDelft, and she will also talk about the hydrodynamic modeling for floating offshore wind turbines. Likhitha, the floor is yours.
Thanks, Axel. Can you see the presentation?
Yes, we can. Yeah.
Okay. Some issues.
We can see it well, but I don't know if on your hand.
Yeah. Okay. Yeah. Can you see the presenter view or the slideshow?
No, we can see the full screen. Yeah.
Okay, thank you. Thank you, Axel. Hello, everyone. Today, I'll be talking about hydrodynamic modeling of floating offshore wind turbines. I'm a PhD student at TUDelft, and I'm working mostly on high fidelity modeling of floating platforms. This PhD is a part of STEP4 Wind Industrial Doctorate Program, which is funded by Horizon 2020. With TUDelft on the academic side, ORE Catapult are my industrial partners. I'm supervised by Axel from TUDelft and John and Daniel from ORE Catapult. So talking about the outline of my presentation, I'll first go over the motivation for this research. Why do we need a high fidelity modeling? And then I'll talk about my research objective. Further, I'll discuss the numerical methodology that will be followed to model fluid structure interactions. With the decline of availability of shallow water sites over the last few years, offshore wind industry has made a transition towards floating offshore wind turbines, which offers great potential to exploit the stronger and steadier wind resources in the deep waters. It also provides easier installation and maintenance capabilities. However, it should be noted that floating offshore wind turbines are more expensive compared to fixed offshore. One way to reduce the cost is to optimize and standardize the design of the offshore structure so that these can be mass manufactured without considering the conditions. But the system becomes extremely complex to standardize because of the fact that there is a complexity in the form of motion of the platform, which is also subjected to the waves and current. It also involves mooring effects and soil interactions at the seabed, in addition to the rotor aerodynamics. Therefore, the modeling and design tools to capture the physical behavior of the system is extremely important. And with this project, I'll focus on developing and improving the hydrodynamic modeling tools for floating structures. Talking about the motivation, it's important to understand the applicability of engineering models. In morning keynote session by Manuel highlighted the different engineering models used, so I won't just go into much detail, but most engineering models are based on potential flow theory, or Morrison's equation, or a combination of both. So Morrison equation includes a drag and inertial effects, and this is only applicable to very slender structures. For potential theory, it is valid for larger structure where your diffraction and radiation effects become prominent. If I draw your attention to this graph here, you can see that it's a plot between Coulligan-Carpenter number versus diffraction parameter. Kc number is a ratio of drag and inertial force. So basically, higher the Kc number, the more is your drag, and lesser the inertial force. And also for a semi-submersible model, there are different diameters involved, because of which each of the subcomponent lie on different regions on the graph. Here it can be seen that, for example, if you go for pontoons, so for modeling this, you would need to use something like a Morrison's equation. And when you go for a base columns, here your diffraction effect is more dominant, so you'll have to go for something like a potential flow model. And it should also be noted that the interaction between these individual components, when considering these models, are ignored and are not considered. Therefore, there have been a series of code-to-code comparison projects which have been conducted by IEA Task 30. One such project, OC5, has revealed that some of these tools tend to underpredict the hydrodynamic loads and motion, mainly at the low frequency ranges. which will affect the surge and pitch motions due to their natural frequency lying in that region. Therefore, to understand this nonlinear hydrodynamic behavior, it is important to rely on the CFD modeling. Now with CFD modeling, they tend to be more computationally demanding, and hence both in terms of time and resources, and hence the computational cost has to be tackled as well. So the main research objective of this project would be to develop a CFD solver for OC5 deep sea wind semi-submersible, and then to implement mesh adaptation technique to tackle the cost issues. The mesh adaptation technique will be used to refine, dynamically refine the mesh where it is required, and then keep it coarse at the other regions. Further, it would be this project can be extended to study of fully coupled aero-hydro simulations or a mooring line model. Now talking about the numerical model. For this project, I'll be using an AILS2 solver, which is an LES-based solver. It's mainly developed at Korea Labs in France. It uses fourth order finite volume spatial discretization scheme, and it uses a fourth order Ranjit-Kutta time integration method. It is mainly used for unstructured meshes, while it supports structured meshes too. It has the adaptive grid refinement capabilities, and it's also massively parallelized. The choice of AILS2 was mainly because of its good parallel scalability. In this figure here, you can see the scalability test performed by Korea with a Blue Gene supercomputer. It can be noticed that as the mesh size increases, the scaling is pretty linear up to 329 million tetra cells. And even after that, it shows pretty decent scaling. Apart from that, as I previously mentioned, it also has the mesh adaptation capability, which can be used in this project to tackle the computational time. And then AILS2 also has a fully validated actuator line model to understand the rotor aerodynamics. And it is also being used by my colleague who is responsible for aerodynamic analysis in Offshore Wind. So in future, if coupling is considered, it would be easier to integrate these two models. Now let's talk about the modeling techniques used for fluid structure interaction. Firstly, I'll introduce a few methodologies that I used to handle the flow dynamics in this particular project. In the fluid domain itself, there are two important things to be modeled. The first one is the movement of the fluid and the movement of the semi-submersible platform. Here, the platform is considered a rigid body, and the fluid structure interaction comes from the interaction between the moving platform and the surrounding fluid itself. The fluid structure interaction here is modeled using an arbitrary Lagrangian approach. The next thing to be focused on is an air-water interface. The two-phase flow solver in AILS2 uses an incompressible Navier-Stokes solver, which is coupled with a level set method for interface tracking. I'm not sure about the background of the audience, but I will go ahead and spend my next two slides explaining the ALE and level set methods a little bit to give a context. So what is an arbitrary Lagrangian method? Most of you might be familiar about the Lagrangian and Eulerian algorithms. Lagrangian algorithms are mainly a particle tracked algorithm. So for example, here, if you can see the mesh node, which is circular, and triangular element, which is a particle, at some time, at the initial time, are coinciding. And for Lagrangian description, it follows that as the particle moves, the mesh also moves to that position. The Eulerian description, which is mainly used in fluids, here the mesh nodes are constant and the particles can move independently. Now there's an ALE description where the computational mesh and particles can move independent of each other. Why do we need ALE approach? It's mainly because of the drawbacks of Lagrangian Eulerian. For Lagrangian, as you can see here, this element, which is a 1D element, as the particle keeps coming closer, the element gets skewed. So it can't handle larger deformations. When it comes to Eulerian algorithms, they fail to track the interface properly. That's why we need a compromise between these two methods, which is an ALE description. And now talking about level set method, as I had explained previously, level set method is an interface tracking algorithm. So for example, if I have two fluids, which is 1 and 2, and this is the interface, so I define a function phi of x, which tracks the interface. Putting these two together, now we have, for my fluid structure interaction, I use a partition method where both the a fluid solver and structural solver work independently, and they pass the values at the interface. So for a fluid domain tool, I use an ALE approach. So these are the equations which govern that. So that's an incompressible Navier-Stokes equation. The only thing different from a normal equation is that here you're considering the relative motion between the fluid and the particle in the advective term. And then for the structural domain, it's again an finite element method model, and the governing equation is given mass into acceleration plus by this equation where F is a force vector and K is a stiffness matrix, M is a mass matrix, and C is a damping matrix. So here at the interface, there will be an exchange of information from fluid to structural domain. Mainly the fluid gives force as the input to the structural domain structure, and the structure gives the displacement as the input here. Now I would like to conclude this presentation by just giving an overall overview of the code development, how it is going to happen in this particular project. Yeah. So there is an ALE solver and a two-phase solver. ALE is the mesh movement solver, which I was talking about. It's present in ALES 2 already, and this is being coupled to form a solver which is two-phase solver with mesh movement. So it can handle the two-phase flows and the mesh movement. Then there's a structural mechanics solver, which is being integrated into this so that we can perform fluid structure interactions with the two-phase flow. And then it will be validated with this particular setup, which you can see here on the screen. It's a very simple setup for an with air and water interface here and a 2D box performing heave in this particular thing, but we can perform any other free decay simulations in heave, surge, or sway. And the project right now is at this stage of validation. After the validation, the idea is to add a wave maker module or a wave generator module to the thing to understand the wave structure interactions overall for the platform. In addition to this, a mesh adaptation can be included at any of the stage of this development to see if addition of mesh adaptation would lead to any computational cost cut down or time cut down. Yeah, so that's my project, and thank you for the attention. If you have any questions, I would be happy to take them.
Thanks a lot, Likhitha. So I think we have a few questions. Maybe Likhitha, if you can stop sharing your screen. Thanks. So maybe I'll start with a question to you, actually, Likhitha. So one question is, does ALE need some specific type of solvers or methods, or is it easy to integrate into any existing CFD solver?
Yeah, ALE doesn't work on its own independently. It just needs one of the Navier-Stokes solvers. As you see, the equation is modified from the Navier-Stokes solver. So yes, it can be integrated to an existing CFD solver by modifying a few equations.
Okay, thanks. Then we have a couple of questions to Manuel. One is, how do you imagine a 3 degree of freedom system with mirroring? How do you imagine a 3 degree of freedom system with mirroring would perform? Would it be sufficient instead of 6 degree of freedom?
Yeah, actually, I think it would be, and I think this was also something that we applied for the cylinder test case, as you have seen. And there was actually a study before already from a student from University of Delft that was finding that especially the heave and the pitch motions were the ones that were heavily coupled, maybe even negligibly even the surge, but you see these are all the motions that are in one plane of motion. So if you restrict it to this 3 degrees of freedom, then I actually think you would cover the most important aspects and could restrain the other 3 degrees of freedom with the mirroring without problems. There may be one exception, and this is if you have a simulation with currents and cylindrical structures, because this then could lead to vortex-induced motions. And actually, our partners from Tokyo have found in tank tests that not only for cylinders, but even for their Oc4 semi-submersible model, this can get excited to vortex-induced motions. So if currents are a thing for you, then you should maybe respect all the 6 degrees of freedom, because otherwise you would maybe miss the vortex.
Okay, thanks for that. Another question for you is about maybe more operation question. So are you analyzing how those differences affect the person working on the platform? Are they significant enough so that with one simulation they can stand up and with the other they will have to stay on the crew vessel?
Honestly, we were not analyzing that at all. Also seen that well, it was for a code comparison, and the experiments were at model scale. So this is really a small model. I think it weighs like 35 kilograms. So there we didn't interpolate up to any accelerations for a full scale model in operational conditions or so. So yeah, I only can say that we didn't take this into account. Sorry.
But that's, yeah, indeed, it's a relevant question, I guess, in practice after.
Yes,
but there would be, yeah.
Definitely.
I see another question for Likhitha. How expensive is ALE in comparison with Lagrangian or Eulerian only methods?
In my opinion, it shouldn't be much. It shouldn't be of a much difference, because the number of equations you're solving is pretty much the same. It stays the same, except that instead of using the entire velocity, you will be using a difference of velocity. So I would say it should pretty much be the same.
Okay. I have a question also for Federica. So you are doing your work on a 2D, right? 2D using a 2D code. I was
Yes.
wondering how much 3D effects are relevant, or yeah, maybe if you can comment a little bit on that.
So I haven't considered 3D effects, but I expect the loads to be a bit reduced because of deep effects. And also the literature hasn't really studied 3D effects, mainly 2D platform motion. And I'm also verifying against 2D CFD, so I haven't quantified the yet, at least, but I think it's interesting to quantify that as well.
Yeah, and you don't see a lot in the literature. That's what you were saying.
No,
right?
not much, because the literature about tidal vertical axis tidal turbines is very limited. So
true. And maybe related to that, I was wondering, well, I see a question maybe that is actually somewhat related to the previous question. So how expandable is the method to 3D? So the panel method, is it easy to extend to 3D, or is it really 2D only?
no, it is possible to extend it to 3D. The same code, for what I know, Professor Freire also already extended it in 3D. Because it was developed during his PhD. And I read his article, and it was both 2D and 3D. So there is already a possibility.
So could be for a follow-up master student, exactly. Perhaps. Nice. I was also wondering more generally, maybe you talked about it in your presentation, but the motivation to go for a vertical axis compared to a horizontal axis tidal turbine. Can you maybe expand a little bit on that?
So I think the main and most interesting reason is that when you have a vertical axis tidal turbine, it's really cost effective in tidal applications as in other applications for installation costs and operation and maintenance, because basically when you have a horizontal axis tidal turbine, you have to place the generator and all the electrical components underwater. So you have to seal them, and then taking them out to make maintenance is very costly. And while instead for vertical axis tidal turbine, you can have them installed above sea level. So above the, yes, so this is, I think, the most, it's the main advantage that it has. Then from the hydrodynamic point of view, maybe a little less, because it's less researched. So of course, you know more about horizontal axis turbines, but and maybe also because of the omnidirectionality is really interesting. If you don't know exactly in which direction the current speed is coming from, and since tides come from the two directions and change continuously direction, that also could be very advantageous.
Mm-hmm. Okay, thanks. There is another question for you, Federica, on the chat, well, on the Q&A. Will your analysis include an estimate on the influence on power production of the turbine with and without wave interaction?
So yes and no. I will look for the influence on power production of the turbine. It's one of the next steps, because we want to see if, so first of all, we want to see if the average power production will be affected because of nonlinear effects. And second, also we want to see if we can exploit the surge motion or the sway motion by tuning the turbine parameter. So optimizing the production with that, but yes, we still have to look into it. And we haven't looked into the wave interaction. I mean, I can simulate it. So the 2D panel code can be used to also integrate wave inflow conditions. But it is very difficult to analyze, because then you have a lot of harmonics superimposing. So you have the inflow conditions, which are not constant, but they are harmonics. And then you have harmonic from rotation, and then harmonic from surge motion. So I tried, but it's really difficult to read, and because of the limited time, of course.
Yeah.
Yes, but you can expect some damping. So the surge will not be, for example, the surge will not be so relevant when you introduce waves, because you have the same frequency and related amplitude, so there is a dampening effect. That's all I can say.
Right, and do you expect, maybe again a bit more generally, that the motion has more or less effect on, let's say, power production with a vertical axis than with a horizontal axis? Or not necessarily, or it's worse? You know, because it interacts as you showed, right, in your little animation. So do you know already, maybe also from what you read, whether you expect better or worse behavior than with a horizontal axis turbine?
So from what I read, for vertical axis, you can have some increase in power coefficient. I don't know compared to a horizontal axis, but I'm sure that compared to a horizontal axis, when you introduce this platform motion, you have more fatigue problems, because of course you have all the wake interaction, especially downwind, but even upwind. For example, if you were like, I showed you an animation of the surge, so the wake evolution of surge, and you can see that even in the upwind region, you have some wake interaction, which before was not really the case. So you have more fatigue problems. So that's maybe some more interesting comparison compared to the power coefficient, at least something that I'm pretty sure about. Yes, more problems about fatigue than about power production. I really don't know. There's not much in the literature.
Okay, thanks. Maybe for Manuel, I was wondering, Manuel, if you saw in your work some issues at the air-water interface. You know, you showed some of the results, and I know from some of the work we've done, sometimes with OpenFOAM, we can have some instability at the air-water interface due to the fact that, yeah, the viscosity, for example, of the air is much lower than water. So it can be numerically more difficult, let's say. Have you seen any of these things or these difficulties when you look at your floater dynamics?
In fact, we had this difficulties rather at the beginning of the project, and it just seemed to be related with some advanced sections actually, and those problems were in Refresco. In OpenFOAM, I think we didn't encounter these problems. Pranav can correct me if I'm wrong there. Yeah, most likely those were related with more of a developer setting in the convection schemes, and after we just changed that, and suddenly our free surface was smooth. Before, we also had like huge numerical artifacts around the free surface, even though we refined it continuously to find if only the discretization is an error. But yeah, this interface is of course always a bit sensitive. But on the other hand, in these decay motions that we are looking at, we are not really creating large waves. We are not like that. There have been tests on the cylinder with waves and moorings, but in the decay tests, like the created wave has like amplitudes in the area of millimeters maximum. So that those are very small motions there, and therefore I think this is not very much a problem. Actually, we have applied even damping zones at the beginning and end of the domain in order to avoid any reflections or whatever. So for this decay test, we really don't want these waves to be there in the end, because they could disturb than anything. So yeah, I think that this problem is coming more up if we then should go for motion of the platforms and waves. Then this is getting more significant again.
Yeah, clear. Thank you. We have a questions a bit for all the speakers, I guess, in case anyone already approached this problem. So some countries only have separate testing facilities for either wave, tidal, and wind. So I guess wave tunnel versus a wind tunnel, but not a facility that combines both. So do you think it is possible to get an accurate model combining the results from both experiments? Is it even possible to combine? I don't know if anyone has some thoughts on this. So I don't know who asked the question, but of course the way floating offshore wind turbines are usually tested experimentally is I think the person is correct. You do either one or the other, but you try to mimic the effect of the missing component, either by a hardware in the loop numerical model. I think we'll touch upon that later this week, or you really place a turbine with some fans and you have a spinning turbine. I'm not aware of facilities that really like have a proper wind tunnel and a proper wave tank. But I guess we will talk a little bit more about that in our experimental testing. I think it's on Thursday. It's Thursday afternoon. I think we have a session on experimental methods. So the person who asked the question, I think it would be good to also be at that. Maybe we can ask it again on Thursday afternoon. And
I think maybe that's the beauty of numerical methods, that we can create a numerical tank test basically, and apply whatever loads and combinations we want, and test very easily or much less expensive than it would be required for an experimental facility. So then it is only getting a question maybe of computational power, but even nowadays with all those huge research clusters, even that is getting less of a problem. So the Oc4 simulations, for example, like for 3 decade periods, you can get results in well 3 days, maybe if it's getting worse 5 days. But still, the cost is quite so much lower than for experimental facilities. So yeah, then only the problem is coming with validation, because usually we don't have the validation data for those test cases available. Therefore, verification, then at least we can estimate accuracy.
I think that's a good note to end on. I don't know if there are any more questions. I don't see any on the Q&A. So if there is no more question, I would suggest to stop here for this first part, and I'd like to thank the 3 speakers again for their very nice presentations. And then I would like to move on to the next part, which is, let me take the program again. So we have again 3 presentations. I'm not sure all the speakers are already there. Oh, I see someone who joined, so that's great. And we will start anyway with Alistair. I think I saw Alistair already, is already a panelist. So Alistair Lee is from Oc4 Catapult, and he will talk about the mooring system design. So Alistair, sorry if I mispronounce your name. Yeah. I think
No, that's perfect. We just get everything ready.
Yeah, we can see the slides. Great.
Great. Well, so that should be all good. So yeah, hi everyone. I'm Alistair Lee. I'm an engineer at the Offshore Renewable Energy Catapult over in Glasgow, working in the floating offshore wind and turbines team, where I'm mainly involved with moorings and anchorings, and largely spend a lot of my time working on the Floating Offshore Wind Centre of Excellence, where the Oc4 Catapult have brought together many developers and future developers of floating wind farms, and together we're running projects to try and de-risk and accelerate the development and deployment of floating wind. So today I'm going to be giving a brief talk about designing a mooring system. I'm going to touch on some of the basic theory, which I think Likhitha, you touched on already, which is good. And then I'm going to be going into some of the tools used and what is currently being done in the industry. And finally, I'm going to just touch on some of the state-of-the-art devices which are being investigated and installed in platforms to date. Come on, there we go. So what is a mooring system? What is a mooring system? I mean, to keep things simple, a mooring system enables the station keeping of the platform. This means that the platform is able to maintain its position, where the mooring system provides a restoring force to platform motions and forces. This can be achieved in a number of ways, which I'll go into explain in a bit more detail in a bit. Whilst we want these platforms to be able to move a bit, we want to, they're not too stiff and the environmental forces allow them to move around a bit. We don't want the platforms to move away too much, as this could result in damage to the export cable or even collision with another turbine and potentially park failure if that happened. So most importantly, this mooring system has to be designed to last a life cycle of a turbine, so around 25 years or more. And the idea of a mooring system isn't new. These have been used extensively in the oil and gas and maritime industry to secure assets to the seabed. Another form of station keeping is through the use of dynamic positioning systems, which use thrusters to maintain position, although these are generally used for temporary assets such as drilling rigs, and it isn't foreseen that these will generally be used in floating wind. So a little bit of the theory, yes, as Likhitha was talking about, when we're solving a lot of the mooring system analysis, it's a mixture between Morrison's equations and diffraction analysis. And you can quite usefully use the Coulomb to Carpenter number to work out if element is going to be dominated by inertia forces or is going to be dominated by drag forces, as can be seen from the Morrison's equation. Now, ideally, we'd want to solve fully coupled CFD analysis, which would require solving all of the Navier-Stokes equations. But this is obviously extremely computationally expensive. So to get around this, we make certain assumptions and use our theories. So, and one of the common ways of doing this is using potential flow theory, where we assume flow is inviscous and irrotational. So if we look at a large piece of the structure, for example, one of the uprights of a semi-sub or a whole bolt, you calculate the Coulomb's carpenter number, you get a low number, which means it's going to be inertia dominated. So when we have that, the easiest way of calculating what the force is going to be is through something called diffraction analysis, where we're solving potential flow theory. So through this, we can calculate we can use panel theory or strip theory to calculate the RAOs of the platform. And then from these RAOs and with C states, which can be random or not, we can then calculate the forces and the displacements on the vessel. If you do get a larger Coulomb's carpenter number, so this might be for the stabilization beams on a semi-sub, or for example, in a mooring line or a riser, then this will be more drag dominated. And so we use quite often Morrison elements in our simulations to calculate the force on these, where the Morrison's equation is calculated to calculate the force. So that gets us our forces on a platform. But then additionally, this is all using linear theory, whereas linear theory states that whilst a water particle will move around in a circular orbit, its average position will be a central point. But if we start to look at nonlinear theory, we start to see that this circular orbit opens up and the particles have a slow moving force taking them in the direction of the progression of the wave. And so this second order moment, the second order force isn't greatly understood to date, but to take into account of this, we calculate what's called the quadratic transfer functions, the QTFs, which tell you how much a platform is going to move, depending on the second order slow wave drift force. And these QTFs are quite complicated for a computer to solve. It takes a lot more computational power. So generally, if we feel we don't want to include them, so we maybe just want to see the effect of an extreme wave on the platform, we don't need to calculate QTFs. We wouldn't bother calculating those so that we can have quicker simulations. Whereas if we're wanting to do long simulations or see the response over a long period of time, for example, if we're doing fatigue analysis, then we'd have to include the second order effects. Now, this can all seem pretty complicated. It's definitely much more complicated than I can do, but thankfully there's lots of tools that can do this for us. And first off, there's simple hand calculations for stuff like catenary mooring lines and the Morrison's equations I've shown before. But then even easier, there's pre-made softwares that calculate these forces in time domain or frequency domain analysis. ANSYS have produced a really great piece of software called Oc4, which can be used to perform diffraction analysis as well as time domain and frequency domain analysis. This comes with a great GUI, and the Oc4 system is very easy to work with. One of the major benefits of this is the pressure forces from the waves can be directly used for FEA analysis on the structure afterwards. Another similar software is Moses, which calculates the same kind of forces, but is mainly text orientated with a simple and not super great GUI as well. But one of the most common pieces of software used in the industry for mooring analysis is Orcaflex by Orkina, which has a great GUI and even has Python API, which you can use to run a lot of batch analysis, etc. Whilst this isn't able to do diffraction analysis, Orkina also produced another piece of software called Orca Wave, which can perform all of the diffraction analysis and get RAOs for platforms. Okay, so then the design parameters. So when designing a mooring system, there's a number of parameters you have to take into account that will affect your design. And taking these from the bottom to the top, but not necessarily the order of importance. First up is your turbine. This will be providing many of the major loads that are driving the forces in your mooring lines due to the thrust produced whilst generating or the drag produced when parked. The floater will then have a large impact on what kind of mooring configuration you can use, as certain floaters will be designed to take certain load paths or may require that certain load paths exist. The water depth, it will have a major drive on the system as the deeper water with deeper water comes heavier mooring lines, and with shallow water comes greater excursions. And with those shallow waters can be quite tricky to prevent uplift on drag anchors. And then the seabed parameters, these largely affect which anchors can be used at the site. So for example, if the seabed is overly hard or maybe even bedrock or extremely soft, then drag anchors or suction anchors might not be able to be used, which are some of the common methods of securing platforms to the seabed. And finally, and most obviously, is the environment. It's always going to be one of the largest drivers of your mooring system. The wind profile seen, the wave heights and periods, both the kind of steady and varying ones, and the extreme waves, and then the current profiles that are seen at the site. And so when we're designing this, what are some of the main things we're designing for? Well, obviously, we want to stop the platform from drifting away. It's kind of main goal. We need to think about what load paths the anchor could take. We've got a drag embedment anchor, for example. We can't see uplift at the anchor because that could compromise the integrity of it. We have to ensure the platform can survive design life in chosen environment. So we have our ULS, ultimate load, where we look at the largest waves the platform can take, the largest wind, etc. Accident load, where potentially we see if a mooring line fails, what effect is that going to have? Can the platform still survive? And fatigue load, you know, if our platform is out there for 25 years, will it survive that? And what design changes can we take so that it's better for that? We obviously have to reduce platform excursions, as I was saying, and prevent snatch loads on the platform, as these can be extremely damaging to connection points. And prevent anchor uplifts, I've mentioned, and obviously, the cost of the mooring lines and anchors and the installation complexity. It's all great creating a mooring system that has very little dynamic effects and is able to maintain for 25 or more years. But if it's going to be extremely expensive and complex to install, then there's not really going to be used by industry. So we have to maintain that as one of the key priorities whilst we're designing our mooring system. So thankfully, oil and gas floating offshore wind doesn't have to start from scratch. And there are many existing oil and gas and maritime examples that we can use, which have been used for well over 25 years. Many of these assets are still installed and operational to date. And whilst there are differences between oil and gas and floating wind, many of these lessons learned can still be used and many of the mistakes avoided. Two good examples of oil and gas productions of mooring systems are the Stone Field and Perdido, whereas these are installed in some of the deepest waters to date, much deeper than we're going to see in floating wind for some time, probably. One of the major differences between oil and gas installations and floating wind is that floating wind farm involves many more assets with many more mooring lines when you're comparing it to a single oil and gas installation. This will affect mooring materials used quite a lot, as it's going to have a large effect on the costs associated with them. So what different types of mooring systems do we have? So there are three main types of mooring an asset to the seabed. The first and most common to date is for the use of a catenary system, where the restoring forces are provided by the mooring lines and their changes in weight. As a platform moves to one side, as it experiences an offset, then more mooring line is picked up off the floor, and this then pulls the mooring line by the platform back to its original position. Second is through a taut system, where the moorings provide restoring forces through their elasticity So with these mooring systems, we're quite often using synthetic ropes for that. And the final system is a tensioned leg system, where the platform is pulled down through tendons. This provides a kind of slightly more complicated system to design, but the footprint of the mooring system is much more reduced compared to especially a catenary system. With the current designs that we're seeing, investigating, we're seeing a lot of combined systems where we're looking at semi-taut systems. Now, this can give the ability of having the benefits of a taut system as well as a catenary system, where we're quite often using buoyancy elements to take ensure that synthetic lines are not touching the seabed, and then we're using clump weights and chain segments to provide more of a restoring force. And this is already, these kind of ideas are already being seen used in the oil and gas industry as well. So some of the standard components you see on a floating wind farm mooring system, this is just an example, and there are many more different types of components and different things that can be added on to your mooring system. The first is the topside connection. Obviously, you're going to have to attach your mooring lines to your platform in some way. With these new systems, we're seeing what we call quick connect systems, which offer the ability to quickly connect a turbine to its mooring and then disconnect them. This will be especially useful when we're looking at heavy maintenance of parts, where we maybe need to install, change out a blade or a transformer, as the platform will be able to quickly disconnect, tow back to port for maintenance. Upper chain sections, we generally use chain in the upper region, or we're looking to potentially use chain in the upper region, as this splash zone could see high damage. The thrash zone around here can be a very damaging area, and obviously there will be more UV damage the closer you are to the surface, and UV damage can be especially damaging to synthetic lines. Load monitoring devices, having a good and accurate way of monitoring the loads in your mooring line allows you to build digital twins, so you can then assess your fatigue loads in the real time and have a strong ability to see if there's any damage to your mooring lines and how long they should be able to last. Synthetic mooring line. So we're quite often seeing in designs coming up more and more use of synthetic mooring lines, as these are much cheaper. Well, they're much lighter to install, and some of them maybe even being neutrally buoyant, and they offer a good level of compliance to the system. Buoyancy supports, as I mentioned, these can be used to lift chain segments or synthetic line off the seabed to ensure that the synthetic rope doesn't have abrasion to the ground. And ground clump weights. These clump weights have been used for FPSO installments in the past, but there have been examples of these failing. And so there needs to be quite a bit more work done looking at the integrity and potential new designs of clump weights. And then ground chain. For our anchors, we want to make sure that there's as much restoring force as possible. So in our ground chain, we're looking at diameters of chain of up to 185 millimeters, which can be around 700 kilos per chain link. And then finally, obviously, there's the anchor. There's many different types of anchors, which can offer different, can take different load paths. One of the most common is a drag abetment anchor, although this can only take a horizontal load path. So if any vertical forces come on, this will compromise the anchor. So as I was kind of mentioning there are different materials you can use in a mooring line, in a mooring system, and each have their pros and their cons. Chain is a very common method. It's being used in oil and gas and the maritime industry for years. You can have a stud chain, which will prevent cross-loading, or you can have a studless chain, which generally has a better fatigue life. These come in varying grades from R3 and R4 up to even R5, and there's talk of some R6 and in the works. The current maximum capabilities of this is about 185 mil, which I was saying is around 700 kilograms per link. This large weight can be extremely beneficial if we're talking about restoring forces, but it can also be a hindrance for installations. With synthetic ropes, the three main types that people are looking at is HMPE, polyester, or nylon. HMPE, one of the main designers of these is Dyneema, so it's quite often referred to by the trade name of Dyneema. And DM10 is one example of that. They have much lower stretch compared to other mooring lines. And so they provide a lot of reduced compliance, which can be beneficial if you do have very deep water. Polyester is one of the most common, used a lot in the oil and gas industry. And nylon is one that's having a lot more investigations now. It offers a lot more compliance, potentially good for shallow sites with the FloatGen project in France using nylon mooring lines. Yeah, these can be very light, can almost be neutrally buoyant in some scenarios, but the high cost installation reels can be a bit of a hindrance. So as you can see on the diagram here, this is coiled around one of the reels, whereas the mooring line itself is expensive. The reel takes up a disproportionate part of that cost. And so if we can see more standardization and reuse of these reels, we can potentially see costs reduce. And then finally, steel wire ropes. Use spiral C-round ropes, and they're light. They have an interesting niche where they're lighter than chain, but not as light as synthetic rope. They're well proven for FPSOs and can be used in catenary and taut system. How much these are going to be used in floating wind is still unknown, although some projects have already ordered to use these in their mooring systems. And future advancements. So there's many things coming online which could help see great reductions in mooring scopes and mooring loads. One of these is load reduction devices, where you can see a number of them here. These act like suspension on a mooring system and take out many of the peak loads and also reduce fatigue loads. So these developers say they can achieve 50 to 70% reduced peak loads and around 30% reduced fatigue loads. And although a lot more qualification needs to go into these devices, there is a large potential for these in floating wind. And we've got new installation aids coming in, which could help with reduced installation costs, such as the tensioning devices you see here. And then this is the seat plate anchor device, which uses a suction pile to install a plate anchor, which the suction pile can then be reused by intermoorer. So there's many more future advancements, especially of these load reduction devices that can bring down the cost of the mooring system. One final one is shared anchors. So if a platform is connected, it uses a shared anchor with another device, this reduces the amount of anchors we need to install, which will massively reduce the cost of anchors, which can be a large driver for the mooring system capex. And you can see the cost of the whole system can go down massively if we're sharing up to 6 lines. Although much more research is needed around the techno-economical analysis of this. And so what happens in the event of a failure, what are the costs associated with that, what happens to the forces on the anchors if there's a mooring line failure. A lot of these questions still need a lot of answers. So yeah, it's been a quick whistle-top tour on mooring systems, design, and some of the future stuff coming on. So yeah, in summary, we want to prevent excursions to the platform so we don't damage the export cable of surrounding assets. We want to provide restoring forces and moments to the platform. And there's well-established analysis from the oil and gas industry, which we can piggyback on for the floating wind. Lots of new potential advancements possible for floating wind, such as shared anchors. And there's many more new design methodologies being proposed. Although with any kind of establishing technology, there's much more research and analysis needed, especially in the area of field tests and proving technology. Okay, that's my presentation. I believe we'll be taking questions at the end. Thanks very much.
Yes, exactly. Thanks a lot, Alistair, for the very, very clear and great presentation. So please post your questions in the Q&A and we'll come back to them at the end of the session. Next, I'd like to welcome Daniel Milano from OREC as well, and he will talk about floating offshore wind design and modeling.
Hopefully you can all see this.
Yeah, we can see, it's not the first slide, I think, but we can see the
No,
presentation.
it's not. Okay, let's try again. Spoilers. All right, better.
Yeah, better.
Good
Thanks.
stuff. Yeah, so good afternoon, everybody. My name is Daniel Milano. I'm an engineer at the Offshore Renewable Energy Catapult in the same team as Alistair. And today I was asked to talk about some design solutions and focus on the hydrodynamics and the physics underlying floating offshore wind turbines. Although obviously this is a very large subject matter, really. We could stay here talking for hours. So I thought I would bring up a few aspects that I thought were more interesting. Maybe some food for thought if anybody was willing to explore further. I will first have a chat with you about some design aspects that concern floating wind, and then transition to some challenges that also need to be addressed. The image here kind of trying to stress the importance of a careful design. Although nobody got hurt in 2016, they were able to right the ship, so to speak, and conclude the project successfully. So floating offshore wind turbines are composed of a floater and a transition piece, which serve as the substructure for the wind turbine, which is installed on top of it. The mooring and anchoring systems for station keeping, as Ali just discussed with us, and the dynamic power cable for grid connection. Now, in 2009, Henderson et al. Performed a very simple but telling analysis about the trade-off between stability and cost, depending on the size of the floater. Intuitively, we can imagine that a small draft and small diameter will have a lower hydrostatic stability, and a large one with a large diameter will result in a higher manufacturing cost. And Henderson proved it using a very simple vertical cylinder floating in a volume of water and piercing the surface. So Henderson also made a step further and looked at different geometries, starting from a slender spar buoy, so a large draft and a small diameter, which he observed was prone to fatigue, whereas a barge structure with a small draft and large diameter would be more prone to major motion responses to wind and waves. There is a third option, which is a small draft and small diameter, typical for tension platforms. And in this case, we are reducing all the motion responses because the entire system is stiffer. And this is, as has been mentioned multiple times today, it's because the stability is provided by the pre-tensioned mooring lines instead of the hydrostatically stiff floating substructure. So modeling and designing a floating wind turbine is a complex multidisciplinary system which encompasses servo aerodynamics, often tackled using blade element momentum theory or heavier and more advanced CFD techniques. The aerodynamics are directly coupled with control systems which control blade, pitch, yaw, and torque. And there is a full coupling between the servo aerodynamic system and the hydrodynamics, which in this case can be computed with potential flow theory and Morrison quadratic drag, again, has been mentioned before today, or CFD. And finally, the mooring system, which again will impact the overall motion and dynamic response of the floating system. During my PhD a few years ago, I looked specifically at TLPs, and I thought I would give you an insight of some of the results. Perhaps not everyone knows that a TLP wind turbine can have a pitching response to wind, or a counter pitching one, as you can see in the images. A pitching response means that the rotor of the wind turbine will be leaning away from the wind, as intuitively would happen. And this is commonly the case for spar buoys and semi-subs as well. However, in some specific geometric configurations, a TLP wind turbine can also enter a counter pitching response to wind, or rather to aerodynamic thrust applied to the center of the rotor. And one of the reasons this can happen, or one of the reasons we can induce the wind turbine to behave counter-pitchingly, if the words exist, as opposed to pitching, is by changing the inclination of the tendons. In the image on the right-hand side over here, we can observe the tendons being vertical at 90 degrees over here. I'll just try to help you out with that. So 90 degrees, it means the tendons are vertical. And as we move towards the left, I am increasingly inclining the tendons. If this is our fancy wind turbine, and these are our vertical tendons, I am then increasingly inclining them like that. And this is the angle that you can see in the x-axis of this image. So interestingly enough, there is a first point where the wind turbine stops pitching at all in response to incident wind. And then there is an entire section or interval within which the wind turbine becomes counter-pitching before switching back to a pitching behavior. And this is solely dependent on the inclination of the tendons, because geometrically a TLP design gives us control over where the center of rotation of the system is, and if it's above or below the rotor nacelle assembly center, it will switch from one behavior or from one pitching direction to the next. Why is this important though? Well, we can imagine when wind blows, in this case in the positive x direction, so from left to right, it will generate a healing moment and a structural moment applied to the tower base. But equally, because the turbine is pitching, there is a gravity-led force due to the RNA combined with the center of gravity of mass of the tower, which will induce an additional structural bending moment on the tower base, and they have the same direction. However, the direction of the gravity-based force changes when the wind turbine is counter-pitching, which can help significantly in terms of the two moments compensating each other. So the question is, are TLPs better than semi-subs and spars then? Because we have this level of control over the design. Well, not so. It's not so simple, not so quickly. Let's see at some hydrodynamic based challenges that TLPs and other floating wind turbine designs have to withstand. So as we all know in this session, hydrodynamic forces are broken down between what the wave exerts on the structure and what the structure exerts on the fluid. Focusing on the wave excitation forces, they are then broken down between Fruth-Krylov forces and diffraction forces, which make up for the total of the non-viscous wave-induced forces. The rest of it, I'm not going to talk about the entire equation of motion, but this is the basics that I need to go where I'm trying to go. So the Fruth-Krylov or incident, and the Fruit-Krylov combined with the diffraction forces in the time domain can be described in the linear wave load model as proportional to the amplitude of the waves, a certain load coefficient, and the frequency of the incident wave. So we can see that in the linear wave model, the force will be proportional linearly to the wave height and will have the same frequency. However, experimental studies have shown that there were observations of high frequency resonant responses to the incident wave and some slow drift forces, which in this case had a frequency that was significantly lower than the incident wave frequency. Why does that happen at all? Why don't we see it in this equation? Well, the answer to that lies in the quadratic wave load model, an equation that we've all seen in primary school, I'm sure. And we can see it's broken down into two parts. The first one, proportional to the square of the wave amplitude, multiplied by a quadratic wave load coefficient called quadratic transfer function, and a sum of two frequencies as opposed to being proportional to one wave frequency. The second part of the equation is the difference frequency QTF, again proportional to a certain load coefficient and the square of the amplitude. But in this case, we use the difference of two regular waves, 2 out of hundreds that can compose our irregular sea state. And this is exactly where the high frequency and low frequency loads stem from. It's from some and different frequency QTFs. And this is all I wanted to talk about. We don't need to dwell into the rest of the equations for now because it's not the focus of my presentation. And I'd much rather spend more time discussing what these effects actually are in nature. So hands-on approach to hydrodynamics, if you will. Well, the high frequency effect is called springing. And because it happens at a high frequency, it only affects TLP designs, whereas semi-subs and spars are quite safe from this point of view. And they are observed when the peak period of the sea state is approximately twice the structure's natural period. And this period interests heave, pitch, and roll, which are in the range between 2 and 5 seconds. And therefore, whenever we have a peak period sea state between 4 and 10 seconds, despite being very far away from the natural period of the rigid body DOFs, it can still affect them. Now, this is another plot from that I published a few years ago, and you can take a look at the dotted lines where I'm comparing the linear with the QTF results, and you can see that a high frequency springing it starts to kick in. So there is an actual effect in it. If you remember from what I showed previously, sorry about that, WTC1 had vertical tendons, WTC4 had significantly inclined tendons. So what I noticed was that on inclined tendon configurations, springing started having a stronger impact in comparison with the non-dotted lines, the continuous lines, where springing doesn't show a very big difference over here. So clearly vertical tendons had less of a, felt a lot less the quadratic sum frequency effect. Difference frequency, on the other hand, is significant, and it can impact TLPs as well as semi-subs and spars. Now, an interesting question that I like to ask when I have these kind of discussions is, what happens if two wave components have the same frequency. Well, the result of the difference is 0. Have you ever seen a wave with 0 frequency? I doubt that. And the way to imagine it physically, it's as if the combination of two waves interacting with each other result in a load that is similar to that of a sea current, so constant and not pulsating. There is a third order effect that I'm not going to show the equations of, but I thought it would still be interesting to discuss. And that is called ringing. Ringing is third order in that it happens when the peak period of a steady state is 3 to 5 times greater the resonant period or natural period of the wind turbine rigid body, meaning that when the steady state peak period is in the range of 9 to 15 seconds, it will affect natural periods in the range of 3 to 5 seconds, which again means it could be a pitch, roll, or heave degree of freedom in a TLP wind turbine. So very much of interest to us. Ringing is highly nonlinear, and it has been observed to be a strong force that happens in a very short period of time. In a way, it's like a hammer that from time to time, almost unexpectedly, slams onto our structure. So it can be dangerous, and it very much needs to be accounted for. Scolan et al. In 1997 defined ringing as a sporadic occurrence, often associated with high and steep waves. And Malenitz and Molan in 1995 have developed an analytical solution for it, showing quite good results in comparison with some basing physical measurements. There is another method called the Fnv method. I'm sure some of you will know it. However, this method has a very limited range of applicability in terms of the size of the structure in comparison with the length of the incident waves. So in terms of second order, there are well-established numerical methods to design and model them. When it comes to ringing, I would argue we are still work in progress. Yeah, I hope this gave you some insight to some of the design aspects that I'm quite fascinated by, and I will be happy to take your questions later on.
Thanks a lot, Daniel, for your clear presentation and passion for the subject. So please ask your questions on the Q&A tab. We have still one last short presentation, and this is by Razieh Jalal Abadi from the University College London. She will talk about larger dissimulation of open channel flow over square bars at different Reynolds numbers. And I think we didn't manage to put Razieh as panelist. So I think the idea is that Pranav shares the slides and then we'll enable her to speak. So that hopefully that will work. Let's see.
I have already enabled her, Razieh, to speak, but Razieh is still muted. So if he or she is there, if they could just unmute to make sure that they are actually here and we can hear them. Not sure. Razieh, if you are here, could you maybe drop a message in the chat, or if there is some technical issue, if you could just let us know. I am not sure for the moment.
Did you try? I think it's a she. Did you try to reach to her by email? Do you have?
Yeah, I did drop her 2 emails, but I haven't heard back. But yeah, I'm not sure what is happening. Maybe we can host a short Q&A session for the other 2 speakers while we figure out what's happening with Razieh.
Yeah, good idea. So Alistair and Daniel will take the question now for you. And I've already seen 2 questions for Alistair on the Q&A. So the first one was, thank you very much for your presentation. Have you heard of wind turbines sharing mooring systems, not only with other wind turbines, but also with other kind of devices, such as tidal turbines, waves, PTOs, etc.?
Yeah, so that's a good question. There's the use of shared anchors is still an area of great research within the floating wind field, because there's a few different factors that affect this. So turbines have to be spaced so far apart so that the rotor, the wind is able to regenerate between each rotor. But with those spacings, the distance between the anchors then becomes quite large. And so there's a study needed into the effect of, does that then make the use of shared anchors redundant, because the costs of you save through losing those through having less anchors, you're then gaining by having longer mooring lines. There's also questions around what happens during the event of a failure. So if one mooring line is to break, and suddenly you've got unstable loads on the anchor, and so the forces on the anchor then might become different to what it was designed for. So I think to date there are, I don't think, any turbines with shared anchors. I believe there's one farm going in that will be using shared anchors. No, I think it's public. Highwind Tampen. They're using shared anchors on their mooring system. So that'll be really interesting to see how that goes in terms of costs saved, and then obviously how that works within the integrity of these assets over 25 years. But the idea of using them with an integrated farm where you have tidal or maybe floating solar there as well, I mean, that's still in the research phase, although, you know, it would be great to see that kind of analysis being done.
I have a little bit of a follow-up question, or related question with shared anchors and mooring lines. So has there been studies on the effect that, you know, do the different turbines start to also be coupled in their motion, or is that not significant enough, you know, when you have shared anchors?
So two turbines that are connected to the same anchor, do they start to then have shared effects?
Somehow, yeah, somehow.
Okay, cool,
yeah.
got you. So that, I mean, I don't really know, but based on my knowledge, I would say it would depend on the mooring system that you're using and the anchors being used. So if you have a catenary mooring system with, say, a suction pile, then I would say that there would probably not be any effects, because the loads when they get to the anchor are generally in the horizontal direction and reduced generally. Whereas if you're looking at a taut system, then the anchor for these shared anchors, they're generally being designed so that the forces will be balanced. And so you get a net zero force on the anchor due to the imbalance of these forces. So yeah, I don't really know. I presume not. And again, an area of a lot of research needed.
Thanks. Another question for you, Alistair, on the Q&A. On one of the last slides that you show, you mentioned prevent platform excursion. By that, do you mean doing O&M operation as much as possible on site and not tow to port, or is that phrase related to something else?
Yeah, so the phrase is related to something else, and people might often call it offset as well. So it's how much the platform moves from its average position, is what's generally called to as excursion or offset. And you want to allow, well, in a lot of mooring systems, you want to allow an area of an excursion so that some of those platform loads are absorbed and can be, the platform isn't too stiff. But if you start to have large excursions, then you are potentially going to damage the export cable, which could lead to whole farm failure if that was significant. In terms of the other aspect of that, looking at the tow to port versus maintenance on site, this is a contentious argument, point that a lot of people will argue quite a lot about. Will people be towing to site? Is it very expensive, especially if you're looking at, for example, spar platforms like the high wind ones, where you could almost mainly only go to the fjords in Norway. It varies a lot, and the way people are approaching this is quite different. But with these quick connect systems, for example, the one I showed was developed by First Subsea, these allow for a platform to be relatively quickly connected and disconnected, so that could make that option a lot more feasible and potentially cheaper.
Thanks. There is another question from Ander, who says, thanks very much to both of you for the amazing presentations. Daniel, you gave very interesting examples related to TLPs. Could you give an overview of similar typical problems to overcome with semi-subs? I had the same question.
Thanks for the question. Yes, I can indeed. I'd be happy to. If you have a few minutes, I can share another.
Sure, please.
The slides are from another presentation. This is related to an effect that I have discussed multiple times in the past. That includes yesterday during the Step for Wind lecture. So I apologize in advance to those who are listening to this for the second time. Ali is probably also sick of me talking about negative aerodynamic damping, but here we are. So negative aerodynamic damping is an aerodynamic effect that impacts all designs, being TLPs as well as semi-subs and spar buoy floating wind turbines. What it does not impact is bottom fixed wind turbines. So this is a very floating wind specific problem. So let's see very quickly what it is. You can imagine wind blowing from the left-hand side over here and straight into our floating wind turbine. Now, a bottom fixed wind turbine wouldn't really go anywhere. However, a floating wind turbine is moored because we don't want it to, drift to Canada or something, but it will have some space to move around. So it will move away from the wind in first instance. Now, the relative velocity that the rotor sees is therefore the difference between the wind speed and the speed of the wind turbine. Say, for example, the wind speed is 14 meters per second, and the wind turbine is moving away at 2 meters per second. Well, the wind speed that the rotor and therefore the controller would see is not 14, however, 12 meters per second. And what does it do in response to that? Well, the controller will pitch the blades according to a wind speed of 12 meters per second instead of 14, which, as we all know, there is a thrust curve above rated wind speed that is decreasing. Therefore, the thrust is higher than it should be, meaning that the wind turbine is pushing, the wind is pushing more than it should on the wind turbine rotor, while the turbine is drifting away from the wind. Then at some point, the mooring lines will decide, oh, wait, this is too far. We will keep you and bring you back. The wind turbine will change direction and start moving towards the wind. At this point, the relative velocity is higher than the effective wind speed. Therefore, on the thrust curve, we are moving over here because the pitch of the blades has been adjusted to 16 meters per second wind speed, again, instead of 14. So as you can see, the wind pushes more, so the aerodynamic thrust is higher when the wind turbine leans away from the wind, and it's lower when it moves towards the wind. And this is exactly what happens when you push a child on the swing. You basically put it into resonance, and the child and the swing will move higher and higher. So the result of that is that the controller is effectively inducing an oscillation into the floating wind turbine where there shouldn't be none, because in this example the wind is constant, and yet we obtain an oscillation like this, where with a constant wind speed. Now there is a number of answers or solutions to that. One is to reduce the control gains. as done in this image over here. You can see the control gains that I used at the time, as opposed to the original gains. You can see they are lower. However, this makes the controller less responsive. In a way, it makes it dumber, if you will. So the efficiency, overall the efficiency of the wind turbine is degraded. So not ideal. High wind, back in the day, when they first noticed this effect, they changed the control strategy from power constant to torque constant. Haven't been able to look into the results, but they claim it worked, and I'm sure it did. What I did, because as I mentioned before, I played with inclining the tendons of a TLP. Yes, I will just mention TLPs for a second. Apologize for that. Well, this is what I did here, right? WTC1 and 2 have vertical or just slightly inclined legs, and there is an oscillation provided by aerodynamic damping here and here. But as I increase the inclination angle of the tendons, well, I end up with a lower oscillation or even no oscillation at all, because I'm increasing the stiffness of the mooring lines on the horizontal plane. So there is a number of different answers to this effect, but it's an effect that needs to be considered during the design phase nonetheless.
Great, thanks Daniel for the detailed explanation on the spot like that. Very nice. There is another long question for you, Alistair. Sorry, that's not for Daniel, indeed, Alistair. So far installations have been performed by mid-size OSVs. Asking from a contractor perspective, do you believe it could be possible and cost efficient to use dedicated installation vessels? For example, using a GUV to install all anchors moorings in one go instead of the OSV during a few trips. Can you also share how is the mooring kept on side and picked up? Is it on a temporary buoy or resting on the bottom before arrival of this foundation?
Yeah, okay, so yeah, good question. Well, a couple of questions. So for that first one to do with installing multiple anchors and mooring lines in one go or doing lots of trips of an OSV, as I see it, there's two aspects to that. So there is vessel availability, depending on where you are. What vessels are available to you will help reduce the mobilization and demob rate. So these the mob and demob rate could be extremely expensive. I'm guessing a JUV is referring to a jackup vessel. The mobilization rate for that could be extremely expensive. And so getting around that and being able to avoid that, whereas an OSV might be a more common vessel type and it might be closer to your port. If you can avoid getting that mobilization rate, then that could be very beneficial. And secondly is the installation rate. So if you take, for example, the Kincardine wind farm as an example, it's maybe not the best example because I think there's been a few problems ongoing, not to mention COVID especially, but it's the installation of that has been delayed. But it's expected that these floating wind turbines will be installed over a slight, for a floating wind farm, potentially over a year or a longer period of time. So there may not be the need to install all assets at the same time. And so if you can use that with your strategy of potentially installing anchors in mooring lines in a just in time philosophy, then that could potentially reduce costs. So I would imagine we'll see more OSVs doing multiple trips, mainly due to vessel availability and the fact that floating wind turbines will be installed over a longer period of time. But if you did have a jackup vessel relatively close to site, so the mobilization rate wasn't going to be massive, and you wanted to get your potentially going into the North Sea or somewhere where there are limited installation windows, it might be very beneficial to do that. So again, like any of these economic aspects, it will be down to very specific for that site techno-economical analysis will be what is the best in this scenario. And to do the second question, how is the mooring kept in sight and picked up? So it depends what kind of quick connect system are being used. You can get topside quick connection systems, and you can also get bottom side quick connection. So some of the quick connection actually connects straight onto the anchor for potentially a taut system. And so in that case, you would just effectively pull up the mooring lines with the platform, and they're transferred together. Or if you have a topside connection, then yeah, a temporary buoy will potentially be used to secure these assets. But again, like I mentioned before, we haven't yet seen tow to site, tow back to port for heavy maintenance in this field. And so this is all very, academic, kind of finger in the air stuff. And what developers actually decide to do when it comes to putting money on the table will be, down to them. So we'll see.
Great, thanks a lot. Thanks a lot for the answers. I don't see any more questions on the Q&A. We did manage to get to contact Razier, but apparently there was some confusion on the time. So I think she expected her talk later. So we'll try to reschedule her on another day of the summer school. So we'll keep you in the loop there. In the meantime, if there are no more questions, I'd like to thank again all the speakers for this session and for the clear discussion and nice discussions we had today. And yeah, I'll look forward to seeing you tomorrow for the continuation. I think we'll start with control tomorrow morning. So looking forward to that and wishing you a good evening in the meantime.
Okay, thanks a lot for coming along, guys.
Thanks.
Thanks.
Bye, everyone.